Welcome back. This is video lecture 21.1, and the title of the chapter itself from our book is Coulomb's Law, which doesn't really tell you much. So let me give you the big picture of what we're doing now. We're making a transition from studying thermodynamics, which is what we have been studying in the last two chapters, to a many chapter unit on what's called electricity and magnetism, both of which are words that, generally speaking, you've heard before. And that really kind of came to its own in the 1800s, okay? Where the phenomenon known as electricity and the phenomenon known as magnetism were understood to be two aspects of one kind of interaction, called an electromagnetic interaction. We'll get there. That's still quite some number of chapters away. We're going to start by focusing on the electricity part of electricity and magnetism because the math is just a little bit easier for that part. And we're going to even specialize further in electricity, at least for the first few chapters, in studying what's called electrostatics, by which we mean that we have a configuration of objects that have a property known as electric charge, and the distribution of that electric charge is not changing with time. So really this first chapter, contrary to perhaps what the title implies, is focused on understanding this property of matter called electric charge. Okay, that's what we're really going to start with here in chapter 21. Okay, so for additional reading, or what I'm summarizing, if you want more content, you go into Wiley Plus in chapter 21 and read sections 1, 2, and 3. In fact, that's all of chapter 21. Section 1 is about what's called Coulomb's law. Section 2 is discussing a property of electric charge called quantization, which I'll discuss. And section 3 is discussing a property of electric charge, charge conservation. Now, we've had conservation laws before, so the fact that another one appears perhaps is not too surprising. I'm, in fact, going to focus on sections 2 and 3 in this lecture. The next lecture will be about section 1. Seems reversed, but that's the way I want to talk about it. Because what I'm really talking about in this video is properties of electric charge. So the first thing you have to understand is that as far as physics is concerned, we consider electric charge to be a fundamental property of matter. Particles, okay? Just like mass is a fundamental property of matter. Particles have mass, okay? Particles can also have this property that we call electric charge. So we're just going to talk about electric charge as if it's a fundamental property of matter. And we're not really going to spend any time talking about, well, why does matter have this fundamental property? Because you could also ask, why does matter have that fundamental property known as mass? And that's a very fascinating and deep question that leads to things like the Higgs boson. But we're not going to get into that now. We're just going to take charge to be a fundamental property of matter, just like mass is. And just like in the SI system of units, mass has a unit, kilogram, then we better give electric charge a unit in the SI system. It's called the Coulomb, capital C. And so you can see that there apparently, you're probably guessing, historically there was an individual with the name of Coulomb who studied electric charge. Bingo, that's right. Okay? So in deference to that person, we call the SI unit of charge the Coulomb. Now, to really understand why a chunk of matter that we might be able to hold in our hand would have electric charge, we have discovered over many years that to really understand why a chunk of matter has electric charge, you do have to have some understanding of atomic structure. Okay? The structure of atoms at the microscopic level. We won't need to go any further than that, any deeper down. Just the structure of atoms. Okay? And the building blocks, the basic building blocks of atoms. So I want to talk just a little bit of review, hopefully this is review, about atomic structure. Okay? And what are the basic building blocks of all atoms? Okay? To discuss that, I'm showing you here a very, very rough, very schematic representation of the simplest atom that contains all three basic atomic particles. Okay? Those three basic atomic particles are an electron, a proton, and a neutron. And the simplest atom that contains all three is, want to guess? I know you might guess helium, but that's not the simplest atom that contains all three of the basic atomic particles. The simplest atom that contains all three is that atom which has one electron, one proton, and one neutron. So if you think about atomic structure, the fact that it has one proton means its atomic number is 1. That identifies it on the periodic table of the elements to be hydrogen. But it also has one neutron. So it's definitely hydrogen, but it has a neutron. Now, the hydrogen you probably learned about doesn't have a neutron, does it? Well, there are these variations called isotopes. And an isotope of an element is one that has a set number of protons, in this case 1 for hydrogen, but can have different numbers of neutrons. No neutrons, 1 neutron, maybe even 2. And so it's the isotope of hydrogen that has 1 neutron is called deuterium. That is the simplest atom that has all three of the basic atomic particles, 1 electron, 1 proton, 1 neutron. So my little structure here is for deuterium. But of course, this picture applies to any element. Okay? You have a very dense, very small, kind of central core-like part called the nucleus. Okay? I'll write that word a little bit larger so it's easier to see. And to give you a sense of scale, here, if I think of it as being roughly spherical in shape, it'll have some kind of diameter to denote its size. Typical nuclear diameter is 10 to the minus 15 meters. Again, I'll write it bigger so that you can see it. To use scientific metric system notation, that's a femtometer. 10 to the minus 15. And in that dense core called the nucleus is where you find the proton and the neutron. Okay? So what are the key things we need to know about the proton and the neutron? We need to know roughly the mass and the electric charge. For a proton, the mass has been measured. I'll give you 3 sig figs. 1.67 times 10 to the minus 27 kilograms. The charge, the electric charge, is said to be positive, and the value is plus little e. I will explain what that means in a minute. But plus little e is the charge of a proton. Then there's the neutron. Its mass to 3 sig figs is 1.68 times 10 to the minus 27 kilograms. Slightly larger mass than the proton, which is very interesting. And its electric charge is 0. It has no electric charge. That is a possibility, but that's where the name neutron comes from. Neutron for neutral. So neutrons and protons in general are found in the nucleus. The electron is then bound to the nucleus via an electrostatic force that we'll be studying. And it's represented in this schematic as this series of blue dots, with some blue dots very densely drawn near the nucleus and then less densely drawn as you get farther out. that representation is actually supposed to represent what's called a probability cloud. Because at the microscopic level, you have to actually use what's called quantum mechanics, and there you have to start talking about, well, what's the probability that if I do an experiment to detect this thing called an electron, I'll find it at a certain location. And you discover that it's more likely you'll find the electron close to the nucleus and less likely as you get farther out. So we just think of the electron as being represented by a probability cloud. Think about that for a while. An electron cloud represents the probability of finding the electron. But if you do detect it experimentally, you find it's like a particle, and it's got a certain mass and a certain electric charge. The mass of the electron is 9.11 times 10 to the minus 31 kilograms. I'm going to write that down. That number is going to be important. Electron mass, 9.11 times 10 to the minus 31 kilograms. Much less than the mass of either the proton or the neutron. Much less. And the charge on an electron is negative, opposite in sign to the charge on the proton that's in the nucleus. And the charge on the electron is minus little e. And the basic size of the electron cloud is about 10 to the minus 10 meters in diameter. So the nucleus is 5 orders of magnitude smaller than the electron cloud. Okay, so we need to have that picture of atomic structure to understand why objects behave electrically the way they do. All right, let's go on with more property of electric, more about this property of matter, I should say, called electric charge. Okay, now the next properties are based on experiment. We're not just kind of fantasizing here. There's been lots and lots of experiments. So here's one property. All charge observed in nature has an integer multiple of an elementary unit of charge. Everything that we detect in nature is an integer multiple of a basic amount. Much like in the United States, our monetary system is quantized in terms of what we deal with when we exchange money with individuals. The smallest unit is the penny. And you can't pay somebody half a penny. Okay? I mean, you can do it on paper, but not in reality, in an actual exchange with another person or a bank. You pay them in multiples of pennies. Apparently, it's been learned by experiment that charge is that way too. Every time we observe charge in experiments, it's an integer multiple of a basic amount. If you want to be fancy and try to impress people, the way you describe that in physics is charge is quantized. There's a basic quantum or amount of charge, and everything is a multiple of that, integer multiple. And in the SI system, we have measured that charge quantum. Well, that would be an important thing to measure. And it's labeled little e. And I'm going to tell you what that size of that is in coulombs. Okay? The elementary unit of charge, little e, is 1.60, 3 sig figs, times 10 to the minus 19 coulombs. Now, the actual number itself, the value of it, is not that deep. Because the number, 1.6 times 10 to the minus 19, is in some sense a function of what system of units we decide to use. It's the fact that the charge is quantized at all that is deep. But please note then that symbol, little e, if you've had more higher level math, that's not the base e of natural logarithms. Okay? It's not that number e. It's just the symbol in physics for the elementary unit of charge. And its value is 1.60 times 10 to the minus 19 coulombs. Now, in general, when we talk about a charged particle in physics, a particle in physics that has this property called electric charge, just like it has a property called mass, and we have a symbol for the property mass, m, that we traditionally use, we have a symbol for the property electric charge. Most books use the symbol Q for that property of matter, known as electric charge. So just like m is a symbol for mass, Q is the symbol for charge. Sometimes capital Q you'll also see. Okay? That. That doesn't mean heat. Sorry, I know we just did that. Different context. But you'll sometimes see that in the books too. Big Q or little q for a label for that property of matter known as charge. Now what I'm saying is that because charge is quantized, the value of Q can only be an integer times little e. And so that's what that formula there is that I just highlighted. Q equals little n times e, where little n can be 0, plus or minus 1, plus or minus 2, dot, dot, dot. Okay? So for an electron, in other words, the value of that integer n is -1, so that Q is equal to -e. For a proton, the value of that integer n is +1, so that Q equals +e. And I could include the neutron. For the neutron, the value of that integer n is 0, so that Q equals 0 for a neutron. All right, now, we will often talk about, in electrostatics, charge being transferred from one object to another. When I do demos in class on Wednesday, the plan will be that we will be in our class, and I will show you some demos where there will be charge transferred, and I will show you in those demos, how I do that. What that often means, this is where the atomic structure comes in, is that when charge has been transferred from one object to another, that often means that it is electrons that have been transferred, and they carry their charge with them. So if I transfer electrons from one thing to another, the thing that lost electrons presumably has left over positive charge, because it's lost some electrons, and the thing that gained electrons have an overall negative charge. Okay? Now, one of the things when you deal with charge transfer, which is indeed a very common process, it's also convenient to talk about the rate at which the charge is transferred. Rate. And if you've had enough physics now, you probably ought to have a little bit of intuition. Say, oh, when they're talking about rate, here comes a derivative. Bingo, here comes a derivative. In fact, I'm going to give you a definition. Electric current is the rate at which charge moves past a point. Electric current. That is a very important property in physics because it is very often true, either naturally or in applications, technology, that we have charge being transferred from one point to another. In the technological case, it's usually through wires, for example. All right, but when charge is being transferred from one point to another, then we can plant ourselves at a certain location and ask, well, what's the rate at which charge is being transferred at by this location, past, okay? And that is called electric current. Now, the symbol we will use for electric current is a lowercase I. That may not be intuitive, but that's what we're going to use. And I, electric current, at a certain location in space where charge is going by, is defined to be the rate at which charge moves past that point. And we'll denote that dq dt. What that really means is, you've got charge being transferred by you in space. You plant yourself at a certain location. And you say, I'm going to count the amount of charge, dq, that passes by me in a certain amount of time, dt. And then I will take the dq and divide it by the dt. And I will call that the rate at which charge is being transferred by me, and I will call that electric current. Okay, now, here we have a new quantity, electric current. It has to have an SI unit. What is that? The SI unit of electric current is called the ampere, also named after a person who studied this. The symbol for the unit ampere is a capital A. And by definition, 1 ampere is equivalent to 1 coulomb per second. 1 ampere of electric current means 1 coulomb of charge is going by you every second. Okay? So just to give you a little bit of practice with the concept of electric current, here's a little quick mini example. When your battery in your car is used to engage the starter motor of the car to get the engine to turn over, there's a conducting path through a wire that carries current of 300 amperes. That's a huge amount of current. But it does that for a rather short period of time, a quarter of a second, 0.250 seconds. And this charge transfer is happening in a wire, and it's happening because electrons are moving in the wire, we'll be learning. So what we want to know is, we want to determine the number, we'll call it little n, of conduction electrons that are transferred by a point in the wire in this 0.25 seconds. All right, this is a very simple mini example. So we're given I, the rate of charge transfer by a point, okay, dq dt. But this is a small amount of time. I'm just going to write it approximately as delta q over delta t, where I'm thinking of the delta t as a small amount of time. And the delta q is the total amount of charge that went by. Now what I really want is just the absolute value, pardon me, of that amount of charge. Technically, electrons have negative charge. I don't care right now about that negative sign, so I'm just going to put absolute value. Okay, where that amount of charge, delta Q, is because n electrons went by in that time, delta T. So n, and then I multiply by the charge of each electron. Well, technically the absolute value of the charge of each electron. So n times E, where n is the number of electrons that went by. And it's that n right there that I want. How many electrons went by my point where I am in the 0.25 seconds? So I write this then as I equals n E over delta t, and then just using algebra, I solve for n. I delta t over E, and now I'm going to plug in the numbers. I am told, is 300 ampere. Remember, ampere is coulomb per second. Little e is the fundamental unit of charge. 1.60 times 10 to the minus 19 coulombs. And, oops, I beg your pardon, I put in the wrong number, didn't I? That was going to go downstairs. Upstairs is delta t, which is 0.250 seconds. That's better. And then downstairs, I have 1.60 times 10 to the minus 19 coulombs. Remember, as I said, ampere is a coulomb per second, so these units all actually cancel. Coulomb cancels coulomb there, and second cancels second. And you just put that in your calculator, see what you get. You're dividing by a very small number, so you're going to get a very big number. It turns out 4.69 times 10 to the 20. No units, it's just number of electrons. That's how many electrons have flowed by that point in 0.25 seconds. Okay, so electric charge is a fundamental property of matter with the unit of coulomb, but all charge is an integer multiple of that fundamental amount of charge, denoted little e. Electric current is the rate at which charge is being transferred past a point. Both those ideas will be used constantly. Now there's a little bit more about electric charge I want to talk about in this video. Again, all of these are empirical. They're shown to be true by experiment after experiment. And here's what we believe to be true. Total charge in the universe appears to be conserved. It doesn't look like the universe is gaining or losing charge. That's a bit subtle thing to try to figure out, but that's what appears to be true. Something we're a little bit more confident about is because we can do tons of experiments, and every time we do an experiment, the following statement is satisfied. The total charge in any physical process is conserved. Any experiment or anything you observe happening in nature, the total electric charge before the event and the total electric charge after the event are the same. I'll give you a couple of examples in nature of how this happens. One example is a phenomenon known as pair production. what happens in pair production? You start with a bundle of electromagnetic energy called a gamma ray photon. The symbol for that is a lowercase Greek letter gamma. And it turns out that the electric charge of a gamma ray photon is 0. Okay? That's a fundamental fact. A photon, a bundle of electromagnetic energy, has 0 electric charge. And what happens under certain conditions in pair production is that the energy and the momentum of the gamma ray photon is converted into actual particles. An electron, with charge, as we know, negative little e, denoted as an e with a little minus sign subscript. But not just an electron, because if that's what happened, a gamma ray photon converted all its energy and momentum into an electron, that would not violate conservation of energy and momentum. It would violate conservation of charge, because I had no electric charge before the event, and I have negative electric charge after. But that's not what we observe in nature. Every time one of these photons converts like this, you see not only an electron, but another particle that we call a positron, which turns out to be what's called the antiparticle of the electron. And the positron has charge plus little e. And it's denoted by the symbol e with a plus superscript, exponent, I guess you might say. Notice then with that, producing an electron and a positron, that total electric charge there is 0. So I had total electric charge of 0 before and total electric charge of 0 after. And over here on the right, it's probably hard for you to interpret what that is, but that's an actual photograph of a pair production event in a detector called a bubble chamber, which is a vat of supercooled liquid that, if disturbed, creates little bubbles. And what happened in this picture is a gamma ray photon came in from the bottom, and at the point right about there, it underwent pair production and produced an electron and a positron. And this bubble chamber is in what's called a magnetic field, which curves the trajectories of electrically charged particles. And the positron goes spiraling off in a big clockwise circle, and the electron goes spiraling off from there in a big counterclockwise circle. And there are the two of them, both the positron and the electron being produced. The pair has been produced. So that's a phenomenon known as pair production, just one of many events that we can see where the total electric charge before the event is the same as the total electric charge after. Here's another example that exhibits conservation of charge: the radioactive decay of unstable atomic nuclei. That happens a lot by multiple mechanisms. But one of those decay mechanisms is known as alpha decay. And I want to show you an alpha decay process that happens naturally in nature. You start out with an isotope of the element known as uranium. It's described as U-238. And all these numbers here, well, the symbol U there means uranium. The superscript 238 is called the mass number of the nucleus. Symbol capital A, it's the total number of protons and neutrons in that nucleus. The subscript number, in this case 92, denoted Z, is the atomic number of the nucleus, and it's the number of protons. So I start out with an electrically neutral uranium atom, and the nucleus had 92 protons. So the charge of the nucleus, right, Q nucleus, is 92E, positive. Now, it turns out U-238 nucleus is unstable, decays by this process known as alpha decay, and what you get out when that happens is two particles. A new nucleus of a different element, and the nucleus of a helium atom, which is called an alpha particle. Okay? So this here, helium-4, is the alpha particle. That nucleus has 4 particles in the nucleus, 2 neutrons and 2 protons, and it has 2 protons, so its atomic number is Z. So the charge of the nucleus on the alpha particle is plus 2e. And then the other nucleus that's created is of the element known as thorium. And its atomic number is 90. So it has 90 protons. And a total of 234 protons plus neutrons. But here I want to focus on the Q of the nucleus. It's 90e. This is what is observed. So what we have in terms of positive charge before, we have 92e in the uranium. And what's the total positive charge after? We have 90e from the thorium nucleus and 2e from the helium nucleus for 92e. So the positive charge has been conserved. Now, it's rather interesting to think about the negative charge, right? Because there were electrons, weren't there also? That uranium atom had not only a uranium nucleus, but 92 bound electrons for a total charge of negative 92e. There presumably had to be negative 92e afterwards, and there is. It's just not denoted in all these numbers. Okay? It turns out the thorium has 92 electrons afterwards. Now that's 2 more than it wants, so it's probably going to lose those 2, but it had them when it was first created. So here's another example of a process that occurs in nature where the total electric charge is the same before as after. Okay, there's really only one more idea that I want to talk about, which will be very important in understanding why we observe chunks of matter having the amount of electric charge they do. And what it turns out that we want to keep track of 2 broad categories of materials. And they are called electrical conductors and electrical insulators. Now, not everything falls into one of those 2 categories, but a lot does. And we'll focus on those 2, electrical conductors and electrical insulators. And we have to be clear what the defining characteristics of each of those are and why they are that way. I'm going to focus on the electrical conductor. Okay? What is the hallmark, the defining characteristic that makes a material an electrical conductor? It is this. The material contains many charges, usually electrons, that are free to move throughout the material. Many free charges, usually electrons. Okay? And as you may be aware already, all elements or compounds or alloys that are called metals are electrical conductors. So some of the metallic elements, aluminum, copper, iron, silver, gold, okay, there are others. Those are all metallic. All metals are electrical conductors. I've drawn here actually a schematic representation of what's called the unit cell for copper, which is a metal, which is an electrical conductor. And what happens in what's called the unit cell is the copper atoms, that's what those little spheres are in a configuration that's said to be face-centered cubic, because you can see there's a cube here. And there are copper atoms at each of the corners, and there's a copper atom in the middle of each of the 6 faces. So that's called a face-centered cubic configuration. And then that structure, that unit cell, is just repeated over and over, one after the other, and that makes up your copper. Now it turns out when you put the copper atoms together in this configuration, the outermost electron, the most weakly bound electron in the orbitals, gets peeled off the copper atom. and can just move freely throughout the material. Every copper atom does that, contributes an electron. Now, a sample of copper that you might hold in your hand is going to contain about, roughly, Avogadro's number of copper atoms. Let's just say 10 to the 23. Huge number, right? 10 to the 23 copper atoms. And in that sample of copper, therefore, you have 10 to the 23 free electrons moving around. Okay? So what you've got is a bunch of free electrons zipping about. I'll just make that like a blob. And then you've got this ordered array. I'll draw a 2D version of it, of copper atoms. Now the corresponding copper atoms are now positively charged because they're actually now copper ions. Remember, each copper atom lost one of its electrons. So I've got a whole, almost like a sea of free electrons roaming around in a lattice of positive ions. And it's this sea of mobile electrons that make the material an electrical conductor. Okay? And that's the important thing we always have to remember when we're dealing with a chunk of matter. We have to know, is it a conductor, an electrical conductor, or an electrical insulator? And if it's an electrical conductor, then we know we have basically an unlimited supply of free charges, free electrons that can move around inside. Now, an electrical insulator is pretty much the exact opposite of an electrical conductor. The atoms or molecules in an electrical insulator do not shed any of their electrons and let them roam around freely. Okay? The binding of the electrons doesn't allow it to happen. And so you don't have free electrons or any free charges roaming around. None. Just the opposite of a conductor. And it's that absence of those free charges that make the electrical behavior of insulators so much different from that of conductors. So as we continue in studying electrostatics, we're going to be talking a lot about the behavior of electrical conductors. And we always want to remember that when we're talking about electrical conductors, it all boils down to the fact that there is this basically unlimited supply of free electrons that are moving around inside the material. Okay, so those are some of the basic properties of electric charge. And in the next video lecture, we're now going to ask the question, let's take two small particles, let's give each of them some amount of electric charge and see if they exert a force on each other because of their charge. And the answer is yes, they do, by experiment. And Coulomb was one of the people who did some of these experiments. So we want to be able to calculate the force that one electrically charged particle exerts on another. And that's the topic of the next lecture. That's all then for this lecture.